My name is Danyang Zhuo. I'm a fourth-year grad student in University of Washington. Today, I'm going to talk about how to lower data center network costs by leveraging its innate path redundancy. A large portion of this work was done when I was an intern in Microsoft Research, working with folks across Microsoft Research, University of Washington, and Columbia University. So if you take a look at today's data center network today, you can see that optics is the main technology for networking. So large bundles of fibers traverse the entire data center room. And the fiber lengths can be quite different when they connect to switches at different places. So I should point out that optical networking is actually very expensive. Besides the fiber you have already seen from the last picture, one of the key contributors to this cost is called a transceiver. Transceiver is a small piece of device that sits between a switch and a fiber that actually transform signals from optical and electrical domains. So in our estimate, optics, including both transceiver and fiber, can cost more than 50% of total data center network costs. Of course, this is just a cost distribution for an example data center network topology. This can be very different depending on the link length distribution, the optical technology choices you have, and the link speed. And this can be as high as 70%. So although the optical layer in the data center network is a significant portion of the cost, nobody has studied this systematically. So in this talk, what we're going to show you is some results from our large-scale measurement of optical links from Microsoft data centers. And what we found is that we observed remarkably conservative state of affairs. What I mean by that is we found those optical links are very much over-engineered. And our idea is simply to reduce the over-engineering by using transceivers beyond their design reach limit. And this approach can give us cost saving up to 40% of the total data center network costs. And the challenge left with this kind of approach is that we will see a small fraction of links have packet errors due to unreliable transmission, and we design and implement a software system called RAIL, redundant array of inexpensive links, that can protect loss-sensitive applications from this packet loss. So before getting into the details of our measurement study, let me give you some background on optical networking. So in an optical link consists of mainly two equipment. One is the fiber, and the other is the transceiver. So a fiber will have two transceivers sitting on both ends of the fiber. So the source transceiver will emit an optical signal into the fiber. And as the signal traverses the fiber, it's going to be attenuated and distorted. And depending on how the other end's transceivers decode this signal, this will map to a certain bit error rate. So the IEEE spec enforces all the communication system to have a bit error rate of less than 10 to the negative 12. So transceivers, depending on how long they want to reach, have very different internal designs. And this makes them cost very differently. So this is a snapshot I just taken yesterday from a transceiver vendor for 10G and 40G technologies. The left two transceivers are for 10G network, and the right two transceivers are for 40G network. As we can see from this webpage, a transceiver has three characteristics. First, it has the type of optical technology it implements. Then it has the design reach limit of how far it can go. And then it has a corresponding price. So we can see building a long link in a data center is significantly more costly than building a short link. So as I have said before, we have done a large-scale study of 300,000 links in Microsoft's data centers. And let me show you some results on the 10G short-reach optical technologies. So the orange vertical line is the threshold for receive signal strength to deliver bit error rate of less than 10 to the negative 12 as required by IEEE spec. So this is a CDF of our observed receive signal strength. As we can see, there was a huge gap between the measured receive signal strength and the minimum requirement. In fact, the median signal strength is 6 times more than what is required. So if we look at the tail of those links with very low received signal strength, we found them to be uniform randomly distributed. This means whatever is affecting the signal strength such as dirt on optical connectors, fiber breakage. These kind of events happens with a uniform probability on all the links. We've done this study across different optical technology types, including 10G, 40G, and 100G, and we found over-engineering is pervasive in all of them. And this is the same across different data centers we studied and across different transceiver manufacturers. And over-engineering is stable over the time period we studied. So why there is so much over-engineering optics? It turns out that in order to make transceivers and fibers to interoperate from different manufacturers, they have to conform to some optical standard. And at this time, the standard they conform on is called IEEE 802.3. So the basic rationale behind this standard is to ensure every link is reliable even under the worst case operation environment, such as the fiber's quality, connector loss, and dispersion loss. And then the standard will derive some reach limit based on the worst case consumption. So for some use cases, such as telecommunication, which is a major use case for fiber optics, this makes a lot of sense. For example, if you imagine this is your telephone network, connects your workplace and your home. If a link goes unreliable, then your whole communication is not reliable. But data center is a very different thing. Data center have many redundant paths. So if a link is unreliable, you just pick another path for your traffic that requires reliable transmission. So no single link matters anymore. So is there any way to reduce over-engineering and thus reduce the cost of total data center network? So there could be many ways. We explored one way, that is to use transceivers beyond their design reach limit. And in this way, we don't have to modify the hardware of those transceivers. And this can, so let me give you an example. So in the IEEE spec, there was a short reach standard that specifies a transceiver whose reach is 100 meters, and it has a relatively low price. And there was another technology called long reach technology that can span 10 kilometers, which has a much higher price. So in a data center, if we want to build a link that is between the reach limit of those two technologies, the only choice you have is to use the long reach technology, because these are the only two technologies that are specified in IEEE spec for 40G. So that costs a lot of money. So our idea is simply stretch the original design limit of the short reach technology and simply use that at 200 meters. So why can this approach reduce the cost of data center network? So imagine your network has 3 different types of optical technologies: optical technology 1, technology 2, and technology 3. Each of them has a reach limit of R1 and R2 and R3, and with price P1, P2, and P3. So this curve shows how much you have to pay to build a link of a certain length. So if you can stretch the reach limit of technology 1 and technology 2 to R1 prime and R2 prime, respectively, there are 2 opportunities to reduce cost. First, for any link whose length is between R1 and R1 prime, you can now use a lower cost opportunity, technology 1 instead of technology 2. The same is true for any link whose length is between R2 and R2 prime. So the exact cost saving actually depends on the link length distribution and also how much each optical technology can be stretched. So we use a testbed to evaluate how much existing optical technology can be stretched. So this picture shows our 10G testbed. Basically what we do is we concatenate short fibers to emulate a long fiber. We use optical attenuator to emulate random effects such as dirt, whatever effect that reduce the signal quality at the receiver end. And we test packet error rate with line rate traffic and convert it back to bit error rate, since bit error rate is a standard metric for a communication system. This way, we can model the effect of stretching on the bit error rate. So let me show you some results for 40G short reach technologies. We use yellow and green dots to denote the 2 transceivers we studied. Those 2 transceivers are from different manufacturers. And with our measurement, we build a conservative transceiver model that captures the worst transceiver in our experiment. And this model is open source on GitHub. So let me give you some result of how bit error rate change when the short reach technology is applied on a long fiber. So remember, this technology only has a reach limit of 100 meters. In our experiment, we found one transceiver can work even when the reach limit is around 600 meters, and the other transceiver can work even when the reach is around 800 meters. They are different because transceivers from different manufacturers have very different tolerance of signal distortion. But both of them can be significantly stretched. To understand why, we study how much extra signal degradation this system can tolerate. So in the IEEE spec, assuming every other factors are at worst case, this system can only tolerate 1.9 dB of extra signal degradation. And in our system, we found both of the transceivers can easily tolerate up to 9 dB of extra attenuation. This means the signal quality at the receiver end at their design reach limit is significantly better than what is required. So we have done this kind of study for other optical technologies too, and we found reach can be stretched by up to 4x. So all of this will give us some reduction in the network cost. So we model our network cost on a 3-stage cloth network with 512 top-of-rack switches. We use a uniform link length distribution, and we parameterize the max length from 10 meters to 2 kilometers in order to cover data center of various size. And for each link in this simulated topology, we will pick the cheapest technology that can cover that reach. Then we can calculate the total data center network cost by summing up the cost from fiber, transceiver, switch, and energy. When we change the design limit of reach limit of a technology, we simply change the optical technology for each link. So let me give you some results of what the cost saving looks like after the stretch. We assume the network uses a mixture of 100-meter 40G technology and a 10-kilometer 40G technology, since these two are the only two technologies specified in IEEE spec under 10 kilometer. So we study two types of stretch. One is a low stretch that makes sure at least 99% of data center network paths to be as reliable as today, which means every link will have a bit error rate of less than 10 to the negative 12. And the other stretch is the high stretch, which ensures only 95% of data center paths to be reliable as today. And the high stretch will have a higher cost saving than the low stretch. As we can see from this figure, we have three types of region. One region, we have zero saving because all the link lengths, their length is below 100 meters, so there's no opportunity for stretch. And we can see a peak around 300 and 400 meters. That means a large fraction of those links are fall into our stretch region. And the third region, where the cost saving actually decrease when the link length distribution is increased, this is because fiber now dominates the total data center network cost. So all of this comes at a cost at having some links have packet loss. So we study the same effect on the same network topology with 0 to 500 meter uniform link length distribution. And what we found is without stretch, 99.99% of your link will be as reliable as today. When there was low stretch or high stretch, some links becomes unreliable. But we can see the fraction of the links that is reliable is very small. And at the same time, their loss rate for most links are still below 1%. So how do we protect loss-sensitive applications from a small number of low-lossy links? So there are several possible solutions. For example, you can do source routing, let the source server pick a path that meets the application requirement. But this approach is fundamentally hard to scale because there are a lot of information you have to distribute it to all the servers. Another strawman approach you can have is simply using error correction code. But you really have to encode each flow with a per path packet error rate in order to avoid bandwidth overhead, since the path packet error rate has a very diverse range. And that can incur large latency overhead when you error encode for short flows. So in real, we use two approaches to solve this issue. One RIL builds multiple virtual topology, where each virtual topology actually ensures a maximum end-to-end path packet error rate. And since we have different classes of virtual topology on the same physical topology, the higher class virtual topology will have a higher loss rate. And what application do is it simply choose the virtual topology to bind to. And we do, for some higher class topology, we use error correction, and we route with error correction appropriate for the path packet error rate. So let me describe to you what virtual topology is. So this is a topology with 6 switches. The green links have 0 loss, and the orange links have 0.1% link loss rate. So we can build a 0% path loss rate topology by selecting a subset of the links from that physical topology. And if you want a 0.1% path loss rate virtual topology, I can also construct a topology like that. So to support unmodified application, we let server expose multiple virtual NICs where each virtual NIC corresponds to a path loss rate guarantee, or the virtual topology. And applications simply bind to the virtual NIC they want. And when they are bind to a virtual topology that actually use error correction, the flow is transparently error encoded with redundancy level appropriate to the path packet loss rate, and the loss rate is queried from centralized controller. Remember, only long flows are supposed to bind to these kind of topologies to avoid latency overhead. So we evaluated RIL on a small testbed with three-stage closed network. We choose 10G short-reach optical technology for all the links, and our end hosts run TCP cubic. We use a optical attenuator to degrade the link, degrade quality of a single link. This way, we can control the loss rate on that link. RIL on this physical topology automatically builds 2 virtual topology. Topology number 1 does not have the degraded link, and topology number 2 has the degraded link. We compare 3 settings on this small testbed. One is there is no deployment of RIL. Second, there is deployment RIL. Third, in order to separate the effect of virtual topology and error correction, we test RIL without error correction. What I mean by that is I use virtual topology number 1 to protect flows less than 1 megabytes in flow sizes. And we compute flow completion time normalized by performance on a non-degraded network, which means I don't have the optical attenuator on testbed. And we use flow length distribution from prior work. Our results is binned by flow sizes. So this is our baseline because there was no optical attenuator, so all the normalized flow completion time is at 1. So when we put the optical attenuator in, like all the flows with different sizes are all penalized, because some fraction of the flows will traverse on the lossy link. And when we enable RIL, like all the flows are running as if they're running atop a lossless network, even though a large fraction of the traffic is actually traveling on the lossy link. To separate the effect of virtual topology and error correction, we also do the experiment with RIL without error correction. And we use virtual topology number 1 to protect all the flows less than 1 megabytes in size. So here we can see with virtual topology, all the flows with less than 1 megabytes in size are running as if they are running on a lossless network. This is because none of those traffic are actually traveling on that lossy link. But the flows bigger than 1 megabytes in size are still penalized. So in summary, what we have found from our large-scale measurement study is that we have a huge room for cost savings in optics used in data center network. And we have explored one concrete way to reduce over-engineering. That is to stretch the design reach limit of optical links. And this approach can save up to 40% of the total data center network cost. We design and implement a software system called RIL that can protect loss-sensitive applications from this packet loss due to reduction in over-engineering. Thank you, and I'm happy to take any questions.
Questions? Arjun Roy, UC San Diego. If you have multiple virtual topologies, each giving different guarantees for expected loss rate, what's to prevent all of your applications from just choosing the one with zero loss rate?
That's a very good question. So in this work, we didn't specify how you could configure rail. So in reality, in data centers, people do use QoS. So I think people, in general, the data center settings, you are controlled by a single entity, and it's non-malicious. So you should believe the cloud provider or the data center operator to carefully configure the system. That's it. Yeah.
Sanjay from Purdue. This is really nice, and it's a very nice insight that you've found. Have you talked to these vendors, and are they possibly considering offering different classes of links at different levels of availability given your results?
Vendors, you mean transceiver vendors, or?
Yeah, the manufacturers of these optical links. I wonder if you've talked to them about your findings and.
We do talk to them. So basically, they also observe similar over engineering, and some even propose they can increase the reach of their technologies. But it's very hard for them to do to actually remake the transceiver so that the over engineering is reduced, because they want to conform to the standard, basically.
I see.
But when they build the transceiver, you're asking whether it can produce multiple level of reliability on the transceiver?
So for example, one way to take your result forward could be they may offer multiple, they could manufacture the link for multiple levels of availability.
Oh, I see.
So you don't need to do this work of estimating what is the error rate yourself, but perhaps they can manufacture it at different levels of availability for different costs. So you can pick the right.
Yes, I think. I think that might work, but I think all the manufacturers we talk about, they want to conform to the standard. They don't want to build non-standard transceivers or fibers. But if they can conform on something, like have a lower cost, that might work.
Okay. Thank you. Yeah.
Hello, Meredith from University of Michigan. I have a quick question. Can you elaborate on how you have estimated the cost of building a data center? Did you also consider, for example, the cost of building the office and racks and switches? Because you claim that you are saving 40% of
right. I see.
Data center costs, and I want to know what you have included and what you have ignored.
Yeah, exactly. So what I have included is the cost of the switch, cost of the fiber, cost of the transceiver, and the energy consumed by the switch. What I have not considered is maybe the physical infrastructure where you actually have to put the transceivers on. Maybe you have to have like a rack structure.
Yeah, actually, for example, if building a data center would cost me $10 billion.
Right.
And if the total cost reduction is, let's say, $1 million,
right.
then probably, I guess, it would be insignificant compared to the total cost of data center.
I see your point. If you include everything in the data center, such as cooling, like servers, racks, and everything, and the space you have to buy, I think it's the number 40% will be significantly shrinked.
Okay.
That's right. But I think people are building really large data centers, like Microsoft, Google, and Facebook. They're building larger and larger data center, and this trend is always increasing. So even a small percentage of the saving would be important.
And are those switch costs and transceiver costs, let's say, are from Microsoft, or did you just use online resources to estimate?
I just use online resources to estimate.
Okay.
Yeah.
All right, thank you. Let's thank our speaker again.
Thank you.